All right, students, I got a good question. You're getting to the hard ones here. And number 26 has this ideal banking angle. It says, what is the ideal speed to take a 100-meter radius curve banked at 20 degrees? So maybe it's worth drawing a little picture to get us started. And to say, all right, if here's kind of the car, then I would say that one force is the gravitational force. And with a banking angle of 20 degrees, you would have a normal force that's tilted over 20 degrees. And no frictional force is needed when we're talking about the ideal. And so it means if you're not going the ideal, you may need a frictional force either one direction or the other from the tires. Usually people take turns faster than they're designed for, and so without friction they would kind of slide up the hill, and so friction is normally kind of this way. But I probably shouldn't even mention that because this author says, hey, let's just always do ideal cases, and that's good enough for this particular set of understandings. But sometimes I think seeing the frictional force kind of helps here. All right, so there would be kind of my step one. Do I have a good physical picture of what's going on? And I think so. I think what I have is a car that has basically two forces on it. The first one is the weight of it, mg, and the second one is the normal force that is no longer straight up because we banked it. And as a result, we can then say that a component of the normal force is pushing inward, and that is what we are using to make the car turn, not the traction of the tires. So we might not even need any friction if the component of the normal force is just the right amount. And so that's why a free body diagram is our second step, to go from, hey, what's going on in the physical picture to our free body diagram, which then leads to step 3, which I call writing out the equations. And since we're looking at forces, there is an x component and a y component. And I've always recommended, both in chapters 4 and 5, and I'm going to continue here in chapter 6, to say, find out, if you can, what the direction of the acceleration is. And grab a blue pen here somewhere. Okay, here's a blue one. And imagine this thing going in a circle. This is where the physical picture comes into place. Is it would go around at an arc or a circle that would have the center at the same level as the car. It would not be down the hill. That would be a circle that would look like this. But the center's here, so it goes around and comes back like that. And so this is the radius. And we know from this chapter that the acceleration for something goes in a circle is v squared over r towards the center of the circle. So it's because of that right here, I will put then the traditional grid on here, because the traditional grid actually has the negative x-axis pointing towards the center of the circle. And that's my hint to you to make these problems a little bit easier mathematically, is always put one of your axes. It doesn't matter if it's the x-axis or y-axis or negative x-axis or negative y-axis, but put one of them in the direction of the acceleration if you know him. That way, the other one is 0. And the one that you do know, you don't have to multiply by some kind of sine or cosine of it. And so in this free body diagram, I'm going to put a little dot also just to kind of remind myself what is the center of the circle. Now, I hope I didn't color over the two forces too much so that you can still see that I'm going to have one force, the gravitational force, in the negative y direction, so it's going to go over to here. And then the normal force is going to have components, so it's going to have a y component, it's going to have an x component. So, again, this is that first step to number 3, which is to write out the equation. So I'm going to say add up all the forces in the x direction and set it equal to mass times acceleration in the x direction. And over here, I'll say add up all the forces in the y direction and set it equal to mass times acceleration in the y direction. All right. So maybe I'll just kind of look at the two forces. Maybe I'll start with the normal force. So as I look at the normal force, adjacent to 20 degrees, so that's cosine function, is the positive y. So over here, I'd say normal times cosine of 20 degrees is the first piece of the y direction. And again, as long as I'm looking at the normal force, it looks like over here, opposite of 20 degrees. So normal times the sine of 20 degrees. That would be the direction of the force in the negative x direction. So I'll put a negative there when I add up all the force. That's the magnitude and that's the direction. And then plus. So when it comes to this first force, it has a x component and a y component, right? It's up and left. So the left is a negative and the up is a positive. We could do the same discussion with the gravitational force. I'll put a plus 0 because the gravitational force is all down and nothing left or right. So 0 in the x direction and all of it, so I'll put a minus mg. So the full thing, mg, no multiplying by sine or cosine of anything, and negative because that's its direction, equals. Okay. Now, the acceleration in the x direction, that's the direction of the center of the circle, must be negative v squared over r. And I'll say it again. And the point of this chapter was to then use the fact that if something goes in a circle, we know the acceleration. We know it is equal to v squared over r in magnitude, and we know it's directed towards the center of the circle. So depending on how you set up your picture and your grid, that could be in the x-axis or the y-axis, and it could be either plus or negative. And the way I set mine up in this picture, using the traditional grid and the slope going this way, maybe I should have made it go that way so I'd get a positive x, but I set it up so the center of the circle is in the negative direction. Okay. And so that's why I put a negative v squared over r. And then, of course, in the y direction, it's equal to 0. So now we can move on to step 4, which is to solve the math. The math says the normal force then would be equal to mg divided by cosine of 20 degrees. And this might be a good time to point out the normal force does not always equal mg. The easiest cases it does, but there are many cases we've seen where it does not, and this is yet another example where the normal force does not equal mg. And of course, the reason that's helpful is I can now put the normal force into this equation over here. And so I will. But before I do, I'll just point out that there is a negative both on the left and the right-hand term, so I'll cancel them off. And so putting in the normal force, which is mg cosine 20 degrees, and then multiplying by sine of 20 degrees, adding 0, and then putting an mv squared over r, I then have a nice mathematical connection between the slope of the hill, the speed, and the radius. And we worked this one out in class. So you almost could just look up the equation we did, or the author also did it in the book, and just kind of plug and chug. But I find it more intuitive to say, look, it's a few fundamental principles that explain a universal phenomenon. So just write out Newton's second laws and work it out for this case where there's no friction, and you're going to get that equation. Okay? And then that's the question. What is the ideal speed? So we're looking for this V. So it looks like if I move the R to the other side, I would get an R times a G, those two terms. And then sine over cosine is tangents would equal to the ideal speed squared. And so putting those numbers in for this particular problem, let's see. The R, the radius of that curve, let's see, what was it, 100 meters? Yeah, so 100 meters. And then times 9.8, then times the tangent of 20 degrees. And I might just want to take a look. Yep, I'm in degrees. Okay, and so that would be V squared. And then I can take the square root of all of that, and we're looking at about 18.9 meters per second. So at that speed, you can make that turn without the need of any friction, which if it was an icy road, that would be ideal. And even if you miss the speed by a little bit, it still would be great to be going something close to that speed so the amount of friction is small, and if it's icy, you can actually make the turn without slipping. All right. Hope that one helps too.